Assalamu alaikum. Today we are going to discuss the net sensitivity in specificity. Before we begin, there are two modes to calculate net specificity and sensitivity. The first is sequential testing. For example, if we perform one test and we identify a particular set of individuals as positive, and then we refined our understanding by digging down deep and perform another test. So this is called as sequential testing. So we want to assess, so there is a loss in net sensitivity and gain in net specificity values in terms of sequential testing. So in order to understand better this example, what I have in my mind is about if we are performing, let's say, blood sugar assessment for a general population. So let's say the test A is to calculate blood sugar, and then we identify a certain set of individuals as diabetic. But in order to confirm that the individuals declared positive are diabetic in blood sugar, we perform another assay, and that test is called as glucose tolerance test. But it is only for those who are declared positive in diabetic test A. Alright, so this is a sequential testing. In simultaneous testing, what is happening is that, like for example, in this COVID outbreak, a person's swab is being shared in two labs which are performing two different kinds of tests. One is relying on antibody assessment for COVID positivity, and the other one is detecting it as PCR based detection. So both the tests are happening at one single time point from a prime source sample. So this is called as simultaneous testings, and so we want to understand whether there is a gain in sensitivity or there is a loss in net specificity which is going to be assessed. So let's begin our example of corona prevalence in Rawalpindi, which is, let's say, it is 5% prevalence reported in Pindi, and based on antibody based detection assay, which is declared as test A, we assume that the level of this test is declared for 10,000 individuals, and we want to calculate how many of them are declared positive and how many of them are declared as negative. So according to the values we have, 5% prevalence indicated, we assume that there would be, out of 10,000 individuals, there would be 500 individuals which will be positive for COVID, right? Then this 500 value is being actually derived by 5% into 10,000 divided by 100 is equal to 500, shown in pink color over here, while the sensitivity of detecting positive COVID identified by using our test, which is test A labeled over here just to save our time of antibody based detection, the true identification threshold for my test is labeled as 350 individuals will be correctly identified as positive by using this test. So the test A could truly identify 350 individuals as positive. The rest of the individuals which are declared as negative would be 9,500. Out of those 9,500, the specificity assessment says that the 80% individuals will be declared as negative, truly negative. So in order to calculate that value of 7,600, what I am doing, I am just multiplying 80 with 9,500 because the rest of the 500 are declared as positive. So, and then I am dividing it by 100 so that I could identify the numbers. So the numbers you are looking right now in 7,600 is derived from this proportion. So 7,600 individuals. So this is true positive individuals, test is positive, true negative individuals declared as negative. Now, let's assume we need a further assurance that whether the test we have used is actually outrightly identifying these individuals or there is something else going on. So in order to identify this, we perform an additional assay, as we are talking right now about the sequential testing. So let's focus on 350 true positives, plus the test may have identified and declared these individuals 1900 as false positive for COVID-19. So we do an additional screening for the positive declared samples. Have you understand this point? 350 plus 900. So for these samples, we're enhancing and going further for an additional screening, right? So the cumulative total was 2,250 positives were tested further by PCR-based COVID-19 detection as test B, and the sensitivity and specificity for PCR-based COVID detection, we assume it to be 90%, all right? So just to make our life easy, we are calculating both these values on 90%. So this value, 1900, was actually the value which was previously declared as positives, and this value of 350 was also declared as positive in the previous slide. Just have a quick look, 350 and 900. So these both circle lines are actually indicating the set of individuals declared positive by test A. So for test B, when we introduce test B, in order to calculate how many of among these will truly be identified as COVID-19 positive patients, we do the same calculation. 90 into 350 divided by 100 is equal to 315, mentioned here. And for specificity assessment, the value is 1710, which is mentioned over here. The rest of the table is just a simple subtraction. We have done it, right? So this is again the values. If you are confused about 2250, this is the total positivity declared by test A. So for calculation of net sensitivity, what we do, we use 315 divided by 500, that is the total prevalence, is equal to 63%. So a net sensitivity value is mentioned over here. For net specificity, we use 7600 plus 1710 divided by 9500 is equal to 98%. So this is the 7600 value plus this value of the two negatives identified over here. So we increase the net specificity to 98%. So we are particularly sure that the persons who are declared negative for COVID-19 by using test A and test B are truly negative to 98%. For the net sensitivity, the values are decreased since the sensitivity for test B reported was 90%, but it is reduced to 63% on a cumulative base. So this is the advantage of sequential testing. It assures that the persons exonerated from a particular disease are truly exoneration. Okay. So, but if both the tests are conducted simultaneously, it's a pretty straightforward example. So test A, let's say that this is our general population and we are performing two tests at the same time for one individual. So test A is identifying the sensitivity value is 80 and specificity 60. For test B, 90 and 90 are the values which are standing by right now. And let's assume that the example we are presenting over here is different from what we have quoted earlier. So over here, if we are proceeding for, the example is saying that, let's say we are checking up the assessment for sensitivity and specificity, the values will be standing over here like 160. Now this true positive value of 160 is actually been derived by using the calculation, which is pretty straightforward. 60 into what's the total number of positive samples we are observing? The prevalence of this disease, we assume, is that let's say the prevalence of this, there is a disease, and that is, let me change the color over here so that we can be more what you can say elaborated in this regard. So let's say there is a disease, the prevalence of that disease is 20% in the general population, okay? And in order to check whether the disease is present in the study cohort we are using, so let's assume over here the cohort size we are dealing with 1000, okay, 1000. 2, 3, 1000. So the number of individuals over here are 1000. Same over here, both sides. 1000 is the true number of but the disease prevalent in this population is 20%, and we want to assess the results for net specificity and sensitivity by conducting two tests simultaneously at the same individuals. So like it's like if we collect a sample and send it to two different labs performing two different sort of tests for a same disease, okay, at the same time point. So for test A, the sensitivity is 80%, and for sensitivity 80% is, as you can see over here, divide into 200 divided by 100. So that's the value we are going to get. This is the value we are going to get, 162 positives declared over here. So why we are multiplying with 200? Because we know the prevalence of this disease is 20%. So 20% prevalence in 1000 is equal to 200 individuals. So we know that the disease is present in 1000, the disease should be present among 200 individuals, but the sensitivity threshold for test A is 160. It is able to truly identify 160 individuals, and for test B it's 90%. So for 90% individuals, the calculation stands for 90 into, again, the disease prevalence is 200 in among 1000 individuals. So we calculated the value, it stays as 180. So 180 individuals will outrightly truly be identified by test B as true positives. And the similar story for specificity assessment, 60 multiplied by, let's say 60 multiplied by, how many of them are declared disease free? 800, and then 800 divided by 100. So we want to identify the test has a threshold limit of truly exonerating disease-free individuals, and this is calculated as 480 over here and 720 over here. Okay, so these two values are the core values which are being identified based on the prevalence of a disease. Since we know that the disease is present 20%, so 20% disease prevalence is going to tell us that the disease, that out of 1200 individuals are diseased. Okay, so that's a pretty straightforward thing we have done just so far. And now from this we assume that 160 individuals which are declared positive in test A may overlap with test B findings of 180 individuals. Now this is the crux, that the people who are identified as positive against by one test may overlap and should overlap with another test B. Okay, so the net sensitivity calculation says that 90% of test B sensitivity among true positives of test A. Since the test B sensitivity is 90%, so 90 into 160 is equal to 144. So test A and test B common areas, they are able to identify 144 individuals by both test A and test B. So the patients which are uniquely identified by test A are 160, that's the true positives, minus 144 that were identified as a consensus between A and B, 16. Similarly for test B, 180 minus 144, 36 individuals by test B. So when for sensitivity calculation, we assume that 16 plus 144 plus 36 divided by 200 is equal to 98% sensitivity. So we increase the sensitivity by performing two tests, different kinds of tests on the same population. So this is called as net sensitivity calculation. But if you look closely, the 90% of test B specificity among two negatives of test A, the value says that 432 are being identified, declared as positive by both the tests. So it's like a sort of consensus between two tests. You can judge the findings by the color match as well. So this is test A. Let's say this is test A, and this one is the test B. So 430 individuals out of 1000 are those which were exonerated, which are declared negative by both test A and test B. They are common, 432 individuals. So for specificity calculation, we say 432 divided by 800. This is the total population which is disease free. So we say the net specificity calculation is 54%. So you can see a gross decline towards the specificity issue. So this is like a seesaw value. If we increase the sensitivity, we have to compromise the specificity threshold. Okay. So lastly, sequential testing, as we have learned in Against Corona, we first performed antibody assay. We say that there is a loss in net sensitivity value, but there is a gain in net specificity. We will be more sure who are disease-free individuals. But for simultaneously testing, we will increase the net sensitivity. We'll be more sure about the positive number of individuals, but we lost those individuals which are actually disease free. So loss in net specificity is observed. So both these sequential testing and simultaneous testing have their advantages and disadvantages. For example, sequential testing is more prone to be done on general population and for screening assessments. The patients who are being suspected are further used for screening. But for simultaneous testing, this is like a preventive approach to induct as much as population we can for vaccination purposes or any other stuff, depending on the need-based assessment. Okay. Thank you very much for your time and attention. If you have any questions, please feel free to ask.